This gripper can clamp down on a solid cube, hold a grip without bursting it, and even grab a single potato chip without crushing it. It squeezes all through with exactly the force we choose. And the crazy part, this whole thing costs us under $40 to build. Every other gripper that can do this costs hundreds of dollars. So what makes us different? It comes down entirely to how we drive the motor. But to understand why that matters, we first need to see how everyone else builds these. If you've seen other DIY grippers, they usually use servos like these. You just tell it which angle to move to and it moves there. That angular motion gets translated through a mechanism to the gripper's jaws, and however hard the servo pushes is how hard you end up squeezing the object. The problem with this is that you are commanding position, not force. You can't actually tell it how hard to grip. The grippers that can control force usually go a completely different route. They use a BLDC motor driven by an FOC controller. That gives you torque control, which is what we are after. But a good FOC driver is expensive, and it drags the cost of the whole project up with it. So here's the goal we set for ourselves. Build a gripper that can control its gripping force while keeping the whole thing cheap. And the key to pulling that off is the motor we picked. Instead of a BLDC, we are using a plain brushed DC motor, and here's the reason why. DC motors can be modeled as a resistor in series with an inductor and a voltage source that depends on the rotor speed, also known as the back EMF. The torque generated by the motor is a function of the current flowing through the motor, and so by regulating the current passing through the motor, we can control the torque it generates, which would allow us to control the gripping force. This, however, isn't as easy as it sounds. Since the current depends on the motor's back EMF, which in turn depends on the motor's rotational speed, a constant voltage source applied to the motor's terminals results in different current values at different speeds. So to set a constant current, we have to design a controller for this. So here's the plan for designing it. We will first model the motor, pick a controller and tune its gains. Let's start with the model. Our model relates the voltage applied to the current flowing through the motor in the Laplace domain. To keep it clean, we treat the back EMF as an external disturbance instead of baking it into the model. So this leaves us with a simple first order transfer function. This transfer function is a type 0 system, so it has some steady state error. To kill that error, we need a PI controller. The integral term in this controller keeps acting until the error is driven to 0. With the model identified and the controller selected, we can move on to selecting the gains. For that, we use a method called pole zero cancellation. Since the PI controller introduces a 0, if we drop that 0 exactly on top of the motor's pole, the two cancel. This gives us a formula for Kp. But notice Kp still depends on Ki, so we are not done yet. After pole zero cancellation, we end up with a simple integrator. To see why that's such a good thing, let's look at the body plot of an integrator. The magnitude slopes down at 20 dB per decade, and where it crosses the 0 dB line is our crossover frequency. The phase sits at minus 90 degrees everywhere. That flat face is the whole payoff. It means the phase margin stays at a constant 90 degrees no matter where the crossover lands. The phase margin is basically how much extra lag the loop can absorb before it goes unstable. We usually want at least 45 degrees, so the 90 degrees it gives us is a lot of room. But the roll system isn't this clean. There are a bunch of effects we have ignored. For example, there's a delay between sensing the current and updating the PWM, and there's also lag from the current sensor's filter. Effects like this add phase lag that grows with frequency, so our real phase margin ends up lower than the ideal 90 degrees, and the closer the crossover gets to the switching frequency, the worse it gets. So to stay safe, we keep the crossover low. A good rule of thumb is 1 to 2 orders of magnitude below the switching frequency. And that crossover is exactly the number we were missing. Pole zero cancellation only logged in the ratio of our two gains, not their actual size. The crossover is the one extra constraint that fixes that. With it, we can finally solve for Ki and Kp. And that's it. We've got a controller that holds whatever current we ask for. And since current control means torque control, we can control the gripping force. With that out of the way, let's actually build it. As always, We designed a custom PCB for this project. The brain of the board is the STM32G4, the same microcontroller we used in our stepper drivers. It's the chip running the current control loop we just walked through. For the power stage, we are using the DRV8876. This is the part that actually drives the motor. It takes the PWM from the STM32 and turns it into the variable voltage across the motor terminals. It also has one feature that is perfect for us. It measures the motor current and reports it to the microcontroller. That's the feedback signal our PI controller needs, and it means we don't have to measure the current ourselves. We got this board made by this video sponsor, JLC PCB. JLC PCB is our go-to for PCB manufacturing and assembly, and we've been using their services long before we started making YouTube videos. So when we recommend them, we actually mean it. The main reason we use their services is their price. You can get 1 to 8 layer boards for only $2. Ordering is also as stress-free as it gets. All you have to do is just upload your Gerber files, get an instant quote, and place your order. And with their quick turnaround times, the board showed up in about a week. Right now, they've got a promo where new users get $30 off 6-layer PCBs. These PCBs come with free Enoch finish and VIN pad. Links are down in the description, go check them out. Before we commit to the full build, we need to make sure the controller actually works. And working for us means that when we set a specific current, we should get a predictable amount of force. That's what this rig is for. The motor pushes on a lever arm, and that arm presses against a load cell wired up to an ESP32. We read the force of the load cell, and from that, we can work out the torque. Here's what we got. Below about 150 milliamps, the current barely does anything. That's because the motor needs to overcome the friction in the gearbox first. Once we are past that, the torque increases linearly with current. That's exactly what we wanted. Above the friction floor, current is torque, so now we can set any gripping force we like. With the controller working as expected, we can move on to the mechanical design. We need to turn the motor spinning into the jaws opening and closing. The simplest way to do that is a rack and pinion. The pinion sits on the motor's output shaft and the rack sits on the moving jaw. So as the motor turns, the jaw slides. That's the whole mechanism. That's really all there is to it. With the design done, all that's left is to actually make the parts. We are going to do this using the Chidi Q2 with Chidi centers. It's a huge upgrade over our old bed slinger. The first thing we noticed with this printer was how fast it is. It prints up to 600mm per second without sacrificing any print quality. It's also fully enclosed with a built-in air filter. This matters a lot since we live in a tiny apartment. It should also help with printing engineering-grade filament. They also sent us their multi-material unit, the Chidi box. It allows us to print parts with multiple colors, but that isn't the coolest part. The coolest part is the drying feature. We had some old damp spools lying around, so we dried them out and they printed like new with no stringing. If you are interested in checking out the Chidi Q2, there are links down in the description. Now let's put the printer to use and finally build a gripper. With everything assembled, it's time to find out if it actually works. We will grip objects of different hardness, starting with a 3D printed cube. Nothing groundbreaking here. Plenty of DIY grippers can pick up a solid object. The real test is what happens when the object can't take much force. A normal gripper will just keep closing until the grip gives, but ours stop exactly at the force we told it to, so it holds without bursting. Now for the hard part, a single potato chip. Grip too soft and it slips right out, too hard and it crumbles. There's almost no margin here. And it grabs it without crushing it. This is the whole point of controlling the force instead of position. So it doesn't matter how delicate the object is, it closes with the exact force we set. To prove that we can actually control the force, let's increase it to crush the chip. And that's it guys, we built our own force sensing gripper from scratch. Custom board, custom firmware, custom mechanics. And the best part is that it cost under $40. If you want to see more projects like this in the future, consider subscribing. Thanks for watching and we'll see you in the next one.